Good evening. Welcome to Krishna's classroom. In the last lecture, we were exploring the problem. We were trying to prove that Rn slash 0 is if you puncture Rn, delete the 0, the origin of 0 vector from it is connected, is path connected for now we observed that for n equal to 1 this is not. For instance, the Rn R1 slash and this is not path connected. So higher values of n, namely n greater than or equal to 2, we are hoping that the result is true. In fact, it is true. For instance, it's quite visible. If you take R2 and puncture it by deleting 0 from it. Delete this point, 0. Then the rest of the space is path connected. Because you can show that if you can fix any element A here and then take any x here, you can always connect A with any x, no matter where x is, you can always connect it. I mean, that is geometry tells you that it is possible. But then how to give a proof of this? Now we were trying to work out a proof for this. And the problem that can arise is this. Suppose you choose, this is the point that is deleted. See, if you take a given A, now if it is in the first quadrant and in the third quadrant, or you join the line joining 0 and A. Take the entire line joining 0 and A. Now, on that one-dimensional space, 0 occurs. And therefore, if you pick A, then it is difficult to connect the points. Now, if A is the first quadrant, then in the third quadrant. A is in the second quadrant, then the corresponding points in the third quadrant. See, or in other words, what I want to say is that you look at these points, TA, where T is belonging to minus infinity 0. Look at this one. So if you take these vectors, that means you are looking at vectors on this side, then you see that you cannot, these two are not connected along this path, along this line. It's a one-dimensional situation. But then you have a lot of space in R2. So we have to show that, to show that this R2 is path connected, all that you need is pick some A and show that It is path connected to every other element of that space. So any x that you choose, A can be connected, path connected to x. That is what you want to. And these are the things which are not accessible through the straight line segment. So all other points, all other points can be accessed through a line segment. So you see, you have got this one, A x. For any x which does not belong to this let me call L. Or if you want, you can call it L minus. Okay. This is a path. That is clear. So we have to find a path connecting A and X. What is the other way? You first go to some place where you can connect, and then from there you connect this. So what you can do is you can take a point on the coordinate axis which is non-zero, connect it, and then. So for that you have to show that if you take what we have proved is this. Take any x belonging to Rn/0 and the unit vectors E1 and E2. Then both the line segments xe1 and xe2 cannot have one of them may have. So the situation is this: x either zero does not belong to the line segment x1 and or 0 belongs to E1 but does not belong to or these are the scenarios that you have. So this is what we have proved. Only one of these things are possible. That is, if both, what we have proved is that if 0 belongs to the line segment XE1 and XE2, then E1, E2 are linearly dependent. Which is not possible. This is not possible. Now these E1 and E2 are the elements of a basis. Okay, so this is not possible. So this is ruled out. Okay, so what you have is these two cases are possible and this case. The other possibility is what we have ruled out. Now, to complete the proof, what you have to show. Okay. So given, so pick A belonging to zero. That is any A which is not equal to 0. So we show that it is path connected to every element of Rn/C. So without loss of generality, we assume that without loss of generality, assume the line segment XA does not contain 0. That is one possibility. Then we take, then we have gamma t, gamma is a map from gamma t equal to so that gamma 0 equal to A, gamma 1 equal to X, and so that is okay. Otherwise, so we look at the possibility that 0 happen to be on this line. Okay. Okay. So how to get to this? Okay. Okay, now we look at the situation. We know that the line segment E1, E2 0. So let us choose A equal to E1 and X arbitrary, and any X then consider the path E1. If and we choose this, if otherwise what we do is we take path X E2 union E1, and note that zero belongs to X E1 assures that 0 does not belong to therefore this particular path is well defined. Now to get to E1, what we do is, because E1 is the base point that we have chosen. So you combine by so you first go from X to E2 and then E2 to E1. So that defines a path from E1 to X. And this does not contain, so 0 does not belong to so that completes the proof. So in any case, you have a path from E1 to any given X. Therefore, it's a nice result. So we have successfully got a path from E1 to any given. See the picture really, this is what it is. So you have deleted the 0 from there. Deleted the 0 from. Now you have E1, you have these two vectors. Now you choose any X. Suppose you choose an X anywhere here, you can connect it as long as 0 is not. This is the path. And the problem comes when X happens to be, suppose X happens to be here. How to go? If you take this path, then it is going to contain 0 in it, which is not a point in Rn/0. Therefore, what you do? Choose the path from E1 to E2, or the segment E1 to E2, and then from E2 to X. See, if 0 happens to be on the straight line segment joining E1 and X, then it cannot be on the line segment joining E2 and X. This does not carry 0. So what you have is, the other path that you have is given by this one. Go like this, and this is the path. Okay, so that completes the proof of the theorem. Now we have a small result. If you want, you can call it here. Suppose X and Y are metric spaces. And F is a function from X to Y which is continuous. if X is connected, is path connected, then Fx is path connected. So path connected space is mapped onto a path connected space by a continuous mapping. That's the moral of the story. So let us work on that. It's quite easy. This is a very simple thing. Since X is path connected, for any X belonging to X, where X is a continuous function, F from such that f of 0 is equal to a and f of 1 equal to x. Now we claim that, so what we claim now let us pictorially view the scene. This is X, this is Y, and this is your f of x. Now we have chosen A here and its image is Fa. Now you take any x here, its image is fx. Okay, so this is what we have. This is f. This takes it. Now what you have here is a path. There is a path connecting A and S. And this is defined by, see, you have an interval 0, 1 from which there is a gamma. So this is gamma t, this is gamma 0, this is gamma 1. Okay. Now what do? You consider, so this is your gamma. This gamma is a continuous function. Now consider sigma from Well, defined by sigma is defined by what? F sigma is defined by F composition. Okay. So you see that F composition gamma continues. This is from the map. F composition gamma is continuous because both F and gamma are continuous. And you see that sigma t is essentially F of gamma t, and gamma t belongs to x, implies sigma t belongs to fx for every t. Zero. It's a continuous function. It maps the whole thing into fx, and therefore what more you have? You have now f of sigma 0 equal to f of gamma 0, which is equal to gamma 0 is A, and sigma 1 so there exists a path connecting for every x Okay, so we choose as the base point fa. So we choose then a free element is path connected therefore fa is a path connected space. Which implies fx is 1. That completes the proof of it. Now we look at some examples. The first example is R positive This is quite simple because all that you need is look at this function ft defined by r cos t is a continuous function. F CR is continuous. And using this, one can build path from, see, actually what you are working on is this circle. Not unit circle with radius r. So if you start with some point here, you can certainly write down the corresponding equation. For instance, if this is the point, this is the yeah. So you choose say 2 points, one over here corresponding to r theta 1 and r theta 2 in polar coordinates. Then all that you have to do is you can define a map from so we define theta equal to r cos theta so that maps from theta 1 theta 2 here, and going from theta 1 to theta 2 to change over from this to 0 to 1 is a very simple work. Okay, so that I leave. Second example, xy belong to R2 such that x greater than or equal to 0 and this is one branch of the hyperbola. If you recall, this is the just recall what it is. This one. It's going to be something like this. I think can faithful. So it would be something like this. This is the one. So x greater than or equal to 0 is this particular branch that you are talking about. This is curves. Now this point is 1, 0. Okay. Asymptotes are x equal to y and x equal to minus y. Now what you do is you can define. So you see that, look at this one, parametric form, y as a parameter. So you look at this, fy equal to positive square root of 1 plus y square comma y. That describes it. Okay. Now, if you take 2 points on this, something here, something here, then you can always stay on this curve and reach there. What you do? Describe the boundary for. So suppose this point is x y1, call this x. Of course, x can be the corresponding x can be fixed. So you call this x1, y1 and x2, y2. Then you see, you choose y1 to y2 as the parametric. So you can define a function from by, how do you define it? Sigma y equal to root of this is continuous. Okay, that is from y1 to y2, sigma is continuous, and you have the, one can show that gamma of y1 equal to root of, or what you call x1 y1 and gamma of, it's quite easy to show. Now what you do, you define a map from, so you define the linear map Now what do you do? You take sigma, so you take this is sigma. Take gamma as defined as so that, because sigma and tau are both continuous maps, so their composition is continuous, etc. So this is how you work it out. You do the same thing here. We gave an example. Now what I want to assert is this. This is one branch of the hyper. Okay. Now the third example, the hyperbola x square 1 is not path connected. Not path connected. How do we do this? See, the problem is this. So this includes what you have is square minus y square. So these are the branches. These are the two branches, the hyperbola. And look at the point 1, 0 and minus 1. So you have 1, 0 there does not exist a path So let us do this. This is what we are going to assert. That is, so we have let H be then you have 1, 0 belongs to H, minus 1. Suppose there exists a gamma from continuous such that gamma 0 oh, zero. Then gamma t equal to gamma 1 t, two real value equations. Both gamma 1 and gamma continuous implies both gamma 1 and gamma 2 are continuous. If so, what happens? We look at gamma 1. Then gamma 1 is a map from 0, 1 to R, such that gamma 1 0 equal to -1, gamma 1 1 equal to +1. So gamma 1 is a map. Therefore, you see gamma 1 is continuous. And therefore, applying intermediate value theorem, there exists a T belonging to such that gamma 1 T equal to 0. But okay, so you see that if you take gamma, therefore there does not exist a continuous function gamma from 2h such that hence H is not path connected. Now we prove some interesting results. Fourth example, the parabola is path connected. It's exactly as we did the earlier path connected cases. This one branch of hyperbola is path connected. Okay, so it's similar problem. Fifth one, let path connected subsets of a metric space. Then assume it's not happening. Now this is quite easy, because what you do is, suppose this is your x and this is your a, this is your b. There are some common points. So you pick an a belonging to a intersection b. Okay, then it is path connected to, suppose you choose an x belonging to a and y belonging to b, which is not in x, say, then what you can do is, you can use the path connecting a and x, you can use the path connecting a and y, combine them to get a path from x to. Okay, so outline, choose a intersection. Now for any x belonging to a, there is a gamma 1, a and x are path connected. Similarly, for y belonging to b, a and y are now a path is obtained by combining is obtained from by combining the path from x to a and the paths, these two paths. Okay, I mean that's the outline of the, that's simple. So if a and b have at least one point in common, then you see that a union b is path connected and our a and b are path connected. Now immediate applications of this are 6. Take the union of parabolas This is actually combining two problems. Earlier we have shown that the parabolas are path connected. Now you take A to be so the scenario is this. Y square equal to x is this one, and y equal to x square is this one. So you have at least 0, 0 is a common, and there is also this 1, 1 is a common. That is A intersection B is D. Now to combine with, since A is connected, B is connected, it is path connected, and there is a common point. Now apply and the path connectedness of parabolas. So you get this done easily. And another problem of the same class is this. Take, so the next problem is 7. A you take as B you take as minus x. So you see that the situation is have the parabola like this, have the other parabola. This is y square equal to x. So you have the common point 0, 0. So 0, 0. Now, as before, not connected. Okay. So that we make some look at this one. Sn, which is equal to x belonging to such that is path connect. S1 is this. This is S1 in R2. S1. And S2 is the sphere in R3. Okay. So we are saying that they are all path connected. I mean, it is clear, but in the case of N, what happens is worthwhile looking at. So here we just observe that Sn is the continuous image of Rn plus 1 slash 0. Take Rn plus 1 and delete 0 from it. You know that this is path connected. We have already proved this is path connected. Okay. For every n, it is path connected. In fact, we proved Rn slash 0 is path connected for n greater than or equal to 2. But now, see, for all integers, positive integers n, Rn plus 1 plus slash 0 is path connected. What is this continuous image? So continuous image of path connected sets is path connected. That's what we have proved just now. So let us write down the continuous image. Now you see that this is the image. So define okay. Then you see that you can easily check that this is a map. This is continuous. And it's a map from and Rn plus 1 is path connected. And which implies That's the proof of that. So that's very simple. Okay. So we prove a theorem. See, what is this map? This map is the following. See, in R2, this is the unit, this is the one. In R2. This point is not there. So if you take a point X here, draw the radial line. Okay, so you take X divided by norm of X, that will bring it to this. So every point on this radial line is mapped to this. Okay, so see that this is a many to one map, but it's a continuous map. Okay, so that's the point. So you this map along the radial line. Take any X here, map to X by that's the image. Now the next theorem is this. This is the theorem that connects path connectedness with connectedness. Let X be a vector space. Path connected. Then it is connected. Go back to the definition of the. So we start with a function f from be continuous. Arbitrary. Since X is path connected, there exists a map from continuous such that so A is some fixed point. So that is the path connecting A and X. It is there because it is path connected. Now consider this map. F composition gamma is a map from see, gamma is continuous, F is continuous, therefore F composition gamma is a continuous map from 0, 1 to plus or minus 1. So F composition gamma and since it is continuous, the only possibility is that this is a constant continuity of F composition gamma that in turn implies F of gamma t is a constant. So, therefore, we have F of A equal to implies that is F is a constant. Which implies so if X is path connected, then it is connected. Okay, so that completes the proof. Now we get the converse of this, whether it is possible or not. So the question that comes up is, true, because we have already seen an example where a connected space need not be path connected. Okay. What is that? One simple example is it possible to say that is connected imply now we have seen already an example in R1. We have seen that Okay, I will take a look. Or we give a very nice example. Take the example of a let us define A to be the set of all points x B as what is this? This is the y-axis. So this is one set. This is the set B. Now let us mark the set. At x equal to 1, sin pi is 0. At x equal to 2, okay, at x equal to 1, this is 1, 0, and at x equal to 1 by 2, it is going to be sin 2 pi. So it's going to be x equal to half. Then you can get x equal to 1/4, etc. Okay. So what you have is this, as these are the zeros of the function. This is a 0, this is a 0, this is a 0, and so on. This is pi, sin pi, and sin 2 pi, pi to 2 pi, sin pi is 0, and then you have this. So you have a curve going like this. So it will come like this. Becomes very oscillatory here. That is the topologist sign. Okay, this is the topologist sign. So this will denote. Now, what is the nature of this curve? You observe the following. Observe that observe that circle. Continue. And you see that X is connected because you see that A union B is equal to A closure. Why? Because you can get every point of +1 to -1 or every point of P in the induced because if you take a point here, you can find a sequence of points over this which converges to that. Although eventually it doesn't end up with any point here. Although you have A intersection, see that A intersection B is M, but A closure is equal to P. Therefore, which implies A closure is connected, which implies X is X path connected. Now one can show that XY is zero zero belonging to B and by a path contained in so this is a typical case where you see that any point of this can be obtained as a sequence of points on this converging to that. That's why I said A closure is essentially equal to A union. Okay, but what happens is that's easy to work out. Any point you take, you can construct a sequence of points lying on this sine curve which converges to that. Okay, so it's a closure, and this path is a continuous path. See, the sine 1 by x or sine pi by x is y is equal to sine pi by x is a continuous function. It is not defined at x equal to 0, at otherwise it is defined, and it's a continuous path. Therefore, see, but this, if you take a point on this B and try to connect it to any point on A and stay on this path, then you will get a continuous path. Okay, so that's why it is not connected. So I think that's a place where we can stop, and thank you very much for this wonderful evening. and we'll meet again. Thank you very much.